Let's get started. Thank you so much for everybody to coming. I am so excited, and then I am so pleased to share my research, recent work with all of you. So let me share my screen. I cannot share.
Okay, let me introduce you first. Thank you, Noburo. Okay, I was just waiting for that one. Yeah. Hello, everyone, and welcome to today's APSC webinar series. I am Dr. Ashwin Todur Sadashiva, Chair of Learning Analytics and Education Data Mining Special Interest Group. It is my pleasure to introduce today's presenter, Dr. Noboru Matsuda. Dr. Matsuda is an associate professor in the Department of Computer Science at North Carolina State University. His research interests include applications of cutting-edge artificial intelligence technologies to enhance learning, as well as to advance cognitive theories in the sciences of learning. Dr. Matsuda received an MS in Math Education from Tokyo Gakuga University and a PhD in Intelligent Systems from the University of Pittsburgh. He has developed a number of intelligent tutoring systems, primarily in STEM subjects. Dr. Matsuda has been leading the SIM Student project, where the research teams develops an intelligent artificial intelligence that can learn problem-solving skills through guided problem-solving or peer tutoring. He initially started the SIM Student project when he joined the CMU in 2004 for his postdoctoral training. He has since expanded the project into multiple applications, including intelligent authoring, Teachable-agent, and learning simulation. On behalf of Asia Pacific Society for Computer Science Education and Learning Analytics and Education Data Mining Special Interest Group, I warmly welcome Dr. Noboru Matsuda. It is great honor to have him here today to share his insights and groundbreaking work in advancing the theory of learning by teaching through teachable agent technology. We are excited to hear from his extensive experience and innovation research. Over to you, Dr. Matsuda. Thank you.
Thank you. Thanks, Ashwin. Thank you so much for the wonderful introduction. See, here again, I am so pleased to share our recent work with all of you. Thank you so much for attending. So let me then share my screen like this. Ooh, okay, I think I can. I think you'll see now. All right. So yes. So here again, my name is Noboru Matsuda. I do research about application of AI for education. Today, I would like to talk about our long-standing research about teachable agent to understand how students learn by teaching. So hope you actually like my talk. Okay. So the challenge is, generally speaking, when we want to do editorial research. So it is very hard, and it's very costly to run tightly controlled studies in kind of authentic classroom situations. Uh, uh, Collecting actually also fine-grained data is very hard. Conducting the reproducible research is even harder. So these are common issues that everybody knows. So then one solution is actually use simulated learners. So they could be like a machine learning agent that can simulate student learning processes. These simulated learners allow researchers to test specific hypotheses with a precise control. And then we can collect the logging data through those simulations. And then we can also simulate like an authentic learning and teaching processes or learning and teaching environments. So Kurt Van Leen actually back to 1994, he actually said the technology for cognitive simulation of learning is now ripe for application. So I truly believe what he said. And then this is exactly what we are doing. So application of simulated learners, there are very many ways to use simulated learners. like a teacher training, teachable agents, intelligent authoring, like so you teach computer so that computer can teach kids, right? Formative evaluation and prediction, crash test dummy. So this is something I love. So because it's a simulated learners, we can do kind of math science, if you will, right? So otherwise we cannot do with human students. Student modeling for intelligent tutors is something also we can do. Today, I would like to focus on teachable agents. And then our teachable agent is called SimStudent. So we are using SimStudent to actually understand how students learn. It's like it is sometimes called the effect of tutor learning. So there has been many positive observations in the literature that they say when you teach, you learn. Right? Students learn by teaching. However, the underlying cognitive theories of why and how learning by teaching happens is still under the kind of investigation. The teachable agent is a commonly used technique because it is easy to conduct studies. It's a machine we can control, and then we can actually measure a precise the variables. So we can test precise hypotheses using teachable agent. For example, we can test the effect of feedback the teachable agent produces, or effect of the kind of we understand the effective tutoring interactions between human student and teachable agent. We can also understand more like a social cognitive factors like perceptions or motivations on the student side. So our teachable agent here again is called the Finnish student. And then this is a screenshot of our online learning environment that we call A+. So down here, this is an avatar of Finnish student. So you are a middle school student, and then one day you're a teacher in your algebra classroom you to teach Finnish student using this interface, right? So now you as a student, middle school student, right? So you enter a problem here, and then you ask Finnish student, this guy here. Oh, by the way, you can name your Finnish student. In this case, it is named Fred, right? And then you ask Fred to solve this problem. The Fred is actually pre-trained a little bit. So he may be able to solve one-step equation. Okay. However, he may not be able to solve the more like a complicated equation. So in this case, this is a two-step equation, and he may have trouble solving this equation, right? And then if he can solve equation, I mean, if he can perform a step, he does it, and then he asks you if this step is correct or not, right? Or even more like if you agree with what he did or not, right? So you may say, yes, I agree with you, or no, I disagree with you, right? And then sometimes Fred, the asks questions, right? If you disagree, in particular, if you disagree with what the Fred did, right, then the Fred may ask questions, something like this, right? So Fred said, I entered 6/7, right? Do you agree with this movement? And then you said no, right? You said it's wrong. And then Fred said, like something like, but before I put 11 for the result of other 3 and 8, now I put x plus 12/7 for subtract 6/7, and then this equation, which I think is the same thing. Why don't it work? Right? Why doesn't it work? Now here, then you need to actually answer this question by typing your response here. Okay. And then if you submit, then the Fred might say, okay, thank you. Or if your response is not kind of elaborated enough, then Fred may ask you follow-up questions. Um, I have elaborated kind of the slides for this dialogue later. Okay. Now, so when you use A plus, so your goal is not only teach Fred, but you teach Fred so that Fred can pass the quiz. So this is the quiz, right? And then this is the quiz that Fred takes. So you see your semi student passes, solves the problem correctly, like in this case, or you see your semi student fails on solving a problem, like this case, right? Oh, by the way, this guy here is Mr. Williams. Let me back up 2 slides here. So this is Mr. Williams, and he helps you to teach your semi student, right? And in this case, when your semi student takes a quiz, then Mr. Williams actually grades the quiz, right, for you. So green means correct, the red means incorrect, right? And then because this is incorrect here, the rest of the steps were not graded, so it's black. Okay. So now you know your semi student cannot solve this problem. So you may want to teach this problem, right? So then you go back to this tutoring interface and then you enter that same equation here and then you teach. Okay. So that's how you interactively teach semi student. And then this is what this online learning environment look like. By the way, this here introduction video, this if you click on this tab, right? So you will see introduction video. This unit overview here, if you click on this tab, you will see like an online textbook, like a book chapter explaining how to solve equations so that you can prepare for teaching, right? Example tab here, if you click on this example tab, you will see worked out examples on this same interface here. So you have a better idea about how to teach, how to solve equations, okay? So that's the A plus online learning environment. So before I introduce the studies we conducted, let me actually give you a very quick introduction to semi student. Okay, so semi student is a genuine machine learning agent, which is a computational model of inductive skill learning. So it's an induction, right? So the semi student learns skills inductively. So the semi student learns the production from examples. The production sets like where to pay attention, how to make an action, and when to make it, right? So this kind of form, right? They are called the production rules. And then psychology people call this scheme like a production. Okay. So the semi student apply production to actually solve problems. Okay. So just an example. If you actually demonstrate here subtract one for this equation, then semi student may compose this production, or you may say production rule. In this case, it says if left-hand side is polynomial, like this is polynomial, and right-hand side here is also polynomial, then subtract the last constant term of LHS, which in this case is 1, right? So subtract 1, okay? This may be a production that the semi student learns, okay? The question is how, right? So how does semi student learn this? So actually, I built the semi student like almost like the 20 years ago, um, 18 years ago maybe. Very, very many years ago, even before deep learning. So the semi student is a purely symbolic AI. Okay, so we combined like a few different symbolic AI techniques. So I call that like a hybrid AI. So to learn where part like this here, the recognizing left hand side and right hand side. So we use version space technique. And then to actually learn the conditional kind of things here, right? So this is a polynomial, and that is polynomial. This is more like the feature, the like a features, right, of this problem state. To learn this kind of features, we use inductive logic programming. And then for this right-hand side, right, how to do it, like in this case, like a subtract the last constant term of left-hand side. So to actually compose this knowledge, we use a brute force iterative deepening depth first search. Okay. So when we designed the SME student, we made a few assumptions about inductive learning. Okay, so we say the inductive, reasoning happen from examples. In particular, when the students are provided positive examples like do this, do that, and also negative examples like don't do this. Okay. So to make induction, the students need both positive examples and the negative examples. Okay. And then, so like I said, SME student learns production rules, right? So individual production or individual production rule, it can be actually made, right, by generalizing and specializing those examples. Okay. And then also to make induction, the student have to have a prior knowledge. Okay. So this prior knowledge may be a domain dependent features and operations. Okay. Just to give you a quick idea about how Smith learns things, right? So here again, the same example, right? So you demonstrated subtract one here for this problem. So in this case, the student may say, okay, I see 3x, 1, x, and 4, right, in this equation. Okay. So then SME student may say, I wonder where this 1 came from, right? Then SME student makes few hypotheses. Okay. Hypothesis number 1, SME student may say, okay, so this 1 here is basically difference between 4, this 4, and this 3, right? 4 minus 3 is 1. Okay, so this 1 may be a difference between this 4 and this 3. Okay, or similarly may say, okay, so this 1 here is a coefficient of this x, right? Coefficient of this x is 1. Okay? Or similarly may say, so this 1 here is that 1. Okay, which is the last term of the left-hand side. Okay, so now I am very positive all of you may say, stupid, right? It's gotta be the last one, right? It cannot be the first two. You can say so because you know how to solve equations, right? You know the algebra, okay? However, if you do not know the algebra, then you should actually think about all these things, three things, equally likely. So that's the hard part of induction. Okay. When people make inductions, right, from examples, they make lots of hypotheses, competing hypotheses, and then you have to pick one of them. So usually, right, the people actually when people make induction, usually people use the Occam's razor, so they pick the easiest hypothesis. Okay, so in this case, oh by the way, I'm sorry, I jumped too much. So do remember we have to provide prior knowledge to the student. So in this case, those things, halal terms, they are the prior knowledge. So you have to provide those kind of vocabularies, right? Or the ability to recognize these things as a prior knowledge. If you don't know this prior knowledge, then you cannot make those hypotheses. Okay. So given those prior knowledge, you may make those hypotheses and you may pick one of these things. And then you may usually pick the easiest, the simplest one. Okay. So in this case, it is the last one. So that's how actually the sim student works as an AI. When learning the production or when learning cognitive skills, sim student can actually take one of two strategies. The first one is learning through tutored problem solving. So it's like you give sim student a problem and then ask sim student to solve it, and then you provide feedback, or you sometimes help semi student, right, to perform a step. So this is like the active learning. So semi student actually commit to doing, right? So this is also called like learning by doing. Okay. So then you provide explicit negative examples, right? If semi student makes steps incorrectly. Okay. So that's first strategy. The second strategy is you can show the entire solution steps, and then you can simply ask the student to see what you're doing. Okay? So this is like the learning from worked out examples, and then this can be considered as passive learning, right? And in this case, because you only demonstrate correct steps, usually, right? So no explicit negative examples are given. Okay? So each of these strategies, they kind of have a benefit and advantage and disadvantages, right? So semi student need both. Okay. Um, but when semi student is used as a teachable agent, the semi student only commits to learning through tutored problem solving, right? So you give the problem to semi student, ask semi student to solve it. All right. So that's a quick introduction to the technology. So now let's talk about the studies. Okay. So so far in last 15 years or so, we actually conducted the field studies just like this in the classroom. Then so we have like more than 2,000 students participated so far in over 90 business as usual algebra classes. Okay. So then we noticed a lot of interesting things. Number one, we know for sure, or maybe I should have said, our data clearly show that the tutor learning does not necessarily happen spontaneously. So think about this, right? You ask middle school students to teach semi student when they are learning how to solve equations, how come they can teach, right? So on day one, no wonder that the middle school students teach semi student totally incorrectly. And then many middle school students get lost. Okay. Then they teach semi student kind of inappropriately, incorrectly, right? So the learning by teaching doesn't happen spontaneously. Okay. So therefore, number two, therefore we introduced meta tutor. So remember the Mr. Williams, like a teacher agent. So that teacher agent we call meta tutor, because that's the tutor of tutor, right? So middle school student is a tutor for semi student. So this Mr. Williams, the teacher agent, is a tutor of the tutor, so meta tutor. So a meta tutor should actually provide an adaptive scaffolding when human student is teaching a semi student. Yeah. Number three, so it was a little bit surprising things for us, but our data clearly show that the meta tutor or the teacher agent, Mr. Williams, should provide scaffolding on how to teach. It's not about how to solve. Okay, so that's interesting, right? So the human students actually teach semi student inappropriately, so they need to know how to teach correctly. It's not about how to solve equations, because surprisingly, students actually learn how to solve equations by teaching, given they teach semi student appropriately. Okay, all right. So this last part is kind of interesting. Okay. So this is Mr. Williams again, right? So this guy can actually help students to understand how to teach. Okay. However, actually, we conducted study about to understand what kind of scaffolding this guy should provide, right? Um, so this is actually data showing the presence of Mr. Williams, the presence of MetaTutor helps, right? So this is comparing the pre-test and the post-test on how to solve equations, and then the pre-test and the post-test about the algebra concept. Okay, so we compare the learning by teaching with Mr. Williams, teacher agent, and without Mr. Williams, teacher agent. Okay. So this year, there was a difference on post test, right? So the student learned by teaching when they have Mr. Williams, right? When they were teaching. Okay. So this difference is statistically significant. Okay. Then this difference here is not statistically significant. Okay. Even when we see a difference here, still we see the pre-test to post-test difference. Okay. So this difference is significant, but not condition difference. Okay. So this data actually tell us that the presence of meta tutor, when meta tutor provide a scaffolding about how to teach, that helps students to learn how to solve equations. Okay, that's kind of interesting. Okay. Um, the so this is one example of how the Mr. Williams helped the students to understand how to teach. Okay. Um, so this x-axis here is like a chronological progress of the problems the students taught. Okay. The first problem they taught, second problem, third problem. Okay. 10th problem here. All right. This is timeline here. So this y-axis here is actually the rank of the problem they taught. Okay. So meaning it is very, very common that students taught one-step equation here. This one means one-step equation. One-step equation as the first problem. Okay. And then it is very common that by the time of the 10th problem, they actually taught two-step equations, right? So this two is two-step equation. Okay. And then this here is actually shows how they move from one-step equation to two-step equation. Okay. The steeper curve here shows they move from one-step equation to two-step equation quickly. And then this blue line here, meaning they move one-step equation to two-step equation slower than this here, the red line. Red line here is the projection of the students who had Mr. Williams. And the blue here is the trajectory of the student without Mr. Williams. So this data show that when Mr. Williams was available, then student actually moved from one-step equation to two-step equation quicker than those students who did not have Mr. Williams. So this is one example of Mr. Williams helps students to know what to teach, right? How to teach. So they have to teach advanced DI equations. Okay, just an example. All right. Um, uh, so this here, this may be too much to actually show because I have only kind of limited time here, right? So this graph here actually basically compared the type of scaffolding that the Mr. Williams should provide. Okay, BL means baseline. This is the condition, the A plus without Mr. Williams. MC here is the A plus with Mr. Williams, who provided we call this metacognitive scaffolding, meaning it's a scaffolding about how to teach. Okay. P here is it's an A plus with Mr. Williams with cognitive scaffolding, meaning Mr. Williams only helped students to understand how to solve equations. Okay. So MC is about how to teach. Baseline is no scaffolding. C is how to solve equations. Okay. MC plus C here is Mr. Williams who scaffolded both about how to teach and how to solve. Okay. And here, if you see this graph, then you will notice that whenever Mr. Williams provided scaffolding about how to teach, then, oh, I didn't mention here, sorry. So this here is a comparison between the pre-test and post-test. Okay, pre-test, post-test. This is pre-test, post-test. Okay, and then here, that's the difference here, right? So this difference between pre-test, post-test is significant. Same here, same here, same here. And then this difference is larger when Mr. Williams provided the scaffolding about how to teach, right? Here. Okay. Scaffolding about how to solve. It helps a little bit, but not as much as scaffolding about how to teach. Okay. And then if here in this study, we compared three conditions here, if you see these two here, right, surprisingly, so how to teach here, this is how to teach and how to solve. There was no difference between these two, right? Okay. So adding how to solve didn't really help much. Okay. How to teach is all what they needed. Kind of interesting. So if you're interested, then you may, I recommend you to read our recent, the journal paper. Okay. All right. So as a summary, right? So tutor learning does not happen automatically, and then they need the scaffolding about how to teach. Okay. Our data also show the both accuracy of tutoring, and the problem selection affects tutor learning. So the problem selection is actually a key. So students often do not know what kind of problem to teach next. Okay. All right. So now that being said, after 15 years of doing semi-student research, learning by teaching, we've been wondering, right? So yes, the students actually can improve their proficiency of solving equations, right? After teaching a semi student for a few days. That's for sure. However, right, so the current literature in math education says, right, it is not sufficient for students to only learn how to solve problems. They also have to learn to justify their solutions, right? So they have to be able to explain what they are doing. So it is important for students to learn both conceptual knowledge and procedural knowledge. Okay. So we are wondering how we can actually help students to actually uh, uh, improve their proficiency on both conceptual knowledge and procedural knowledge. So that's our recent kind of research focus. Okay. Then we actually this hypothesis. Okay. We hypothesize that if teachable agent asks questions, that actually stimulates student reflection, and students actually commit to that reflective thinking, then the effective tutor learning will facilitate it, in particular to learn conceptual knowledge. Okay, that's our hypothesis. Okay, so that being said, so now the research says, right? So when a student actually commits to explain their thoughts, right? So they do either knowledge building explanations or they do knowledge telling explanations. Okay. So the knowledge building explanations is actually framing kind of underlying uh, thoughts, right? Or their understanding, okay, through sense making kind of the explanations. So that's more like that is called the knowledge building explanations. Okay. Students could also, or maybe students often do knowledge telling explanations. That's a mere kind of recalling or rephrasing of the things they already know. Okay. So when it's about learning by teaching, right? When teachable agent asks questions, okay, student could simply say, you have to do this, which is knowledge telling explanation. Or the student could say, you should do this because, blah, blah, blah. Okay. So that is knowledge building explanation. Okay. So then we have this hypothesis that if the teachable agent can solicit the student, I'm sorry, let me back up. If the teachable agent can solicit the human student's knowledge building explanations, then the students may learn not only procedural knowledge, but also the conceptual knowledge. So that is our the constructive to the inquiry. Okay. So, so in this case, right, so the human student asked, why do I need to perform subtract 2? And the human student said, to simplify the equation. This to simplify the equation is an example of knowledge telling. Okay. So then because this is knowledge telling, the semi student may follow up, right? Like, I understand what you said, but a little more informative reply would be helpful. Can you explain why subtract 2 is your first guess? Okay, blah, 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 right? So this kind of follow-up question is mean to, this kind of follow-up question means, is meant to solicit human students' knowledge building response. Okay, so this dialogue actually kind of goes and goes until either the human student actually commit to the knowledge building response, or the turn taking goes too long, maybe like a 3 turn. Okay, then semi student may actually simply let the student go. All right. So now, right. So the just a summary, as a summary. So semi student asks the initial question. Okay. If the student response is not telling, then semi student may follow up. And then this follow up happens until the human student actually provide knowledge building response. Okay. Now, so then we hypothesize that this kind of dialogue can be implemented using pre-trained large language models. Okay. Because I see I don't have much time, right? I do not commit to the details, but we actually use the stacked LLM. So we use 2 LLMs. Okay. So the first LLM is to actually generate ideal response, like a generate ideal knowledge building response relative to the question, the initial question, right? Like, why am I wrong? Okay. The second LLM is given this problem state and the initial question, and then this target response here, right? And then insufficient response that student made, right? Given those input, this question LLM actually computes the follow-up question. Okay. And then this dialogue goes and goes and goes until the human student actually provides the knowledge building response. Okay. Um, so this is like a research question has been published this year, AIED, right, in Brazil, right? So does assertion enhanced feature learning reduce the hallucination in LLM? So the LLM, using LLM in the classroom is concerning because of this inappropriate behavior, right? The hallucination. Does assertion enhanced feature learning generate high quality knowledge building explanations? So this assertion enhanced feature learning is a technical, details about our prompting technique, right? So to actually reduce the hallucination. Um, because of the time limitation, I don't commit to the explanation about this. So please review this paper if you're interested. Okay. So we actually so we actually asked the in-service teachers to actually validate the performance of LLM. Okay. And then so what we found actually, let me see here. Okay, so what we found is actually the also I mean to show you the student performance here, but I think I incorrectly grab a slide. Sorry. So this slide shows actually the more like a technical engineering the aspect of this research. So this slide shows like if this future assertion enhanced featured learning actually worked better than traditional featured learning. So the answer is yes, right? So this assertion enhanced featured learning actually produced better the questions, better responses. Okay. So when you review this paper, actually, then you will see the result we actually obtained from about human learning. So we actually observed that the current data show that so this kind of the uh, this kind of constructed inquiry did actually help students to actually learn conceptual knowledge. Okay, than without this kind of follow-up question. So if you're interested, please review this paper. Okay, I'm sorry, I just incorrectly grab a slide here. All right, so that's kind of quick overview of our research. Uh, there's just concluding remarks. So the teachable agent for learning by teaching has enormous, I would say, a potential to advance theory of human and machine learning. Rich interaction between the human teacher, student, and teachable agent, right? An essential driving force for the theory development to understand how and when learning by teaching happens. Okay. So we have, like I mentioned, we have more than 2,000 students worth of data. So analyzing this data actually tells a lot of stuff. Okay. So thank you so much. That's about it. If you have any questions, let me know. And then if you're interested, please visit our website here. Thank you.
Yeah. Thank you so much, Dr. Masura. So
So
it's good
should
to,
I stop sharing now? Sorry, should I stop sharing my screen?
yes, I guess.
Okay. Okay.
Yeah, it's open for the questions, so they will come and ask. So it's interesting to know about the teachable lessons again on how to solve, what to tutor, what is reflective thinking, and the few short learnings using LLM and so on. So it's good. So now it's open for the question. Attendees, please, if you have any questions, it's there in the chat. So we can ask questions. Before they show up the questions, if there is not in the chat, I will have a one small question to start with.
Yes, please.
So what are the different modalities that are considered while doing the analysis? Is it just the system log data with charts transcripts or anything else?
Yes. Yes, the question is what kind of data we have and then how we analyze, right? Yes, thanks for asking. So we have the learning outcome data, which is actually pretest post-test score. We
Mhm.
also have the learning process data, which is the interaction between
Mhm.
human student and the sim student, right? The human student and the system. So the process data was automatically logged when students are using the system, right? And then
Mhm.
we do like we can start. Usually we start from analyzing pretest post-test, right? Like the ANOVA right? The t-test kind of stuff, right? And then we then do some kind of correlational analysis or
Mhm.
like a predictive analysis, right? Using this process data. Like for example, right? The number of times student commit to the knowledge building versus knowledge telling, right?
Mhm.
And then we can correlate that with the learning gain, for example,
Mhm.
right?
Yeah.
We can also analyze the response, the text the student actually enter, right? Or the number of times they teach, the number of questions they tutored, right? Um, we can also precisely see the accuracy of their tutoring, right?
Yeah.
So they say, yes, you are right, no, you're wrong, right? So we can compute the accuracy of these. And then sometimes SIMI student gets stuck, and then SIMI student asks students to do next step. And then we can compute the accuracy of the next step.
Yes. Yeah, that's so nice. So one follow-up question is that what is um, did you try actually giving the feedback which are not related to just the content, more like empathy-based feedback, or if some student is getting wrong again and again, if the feedback is just related to their cognitive or the words related to the problem that they are solving, or is there any other types of feedback which generally a human tutor provides?
Right. So the question is, what kind of feedback do students provide or the machine provides?
Machine
The student.
provides.
A
Yes.
machine provides. Right.
Yeah.
So the SIMI student as a teachable agent, right? So the SIMI student can only ask questions, right? Like if human student says, no, you have to subtract four, then the SIMI student may ask, why should I subtract four instead of multiply, right? For example, right? And then the SIMI student has the capacity to actually follow up human student's response, right? That's on the LLM part. Okay. And then
Mm.
the Mr. Williams can provide a proactive kind of suggestions, right? Like, you know what, actually, you better teach this equation instead of what you enter,
Mm.
right? Right. So this quote unquote feedback here is more like the in the form of suggestions from Mr. Williams, right?
Yeah.
Or the follow-up questions from SIMI student,
Yes.
right? Um, right. So the Mr. Williams actually provide the feedback to SIMI student, right? When SIMI student takes quiz,
Mm. Yes.
right?
Makes
So
sense.
these steps are correct, those steps are incorrect, kind of stuff.
Yes. So if there are any other questions, I cannot see in the chart here. So Wong or Alex can help me with that. So if there are any questions which I miss or cannot see, so can you please pop that out so that. Okay, then I will ask one last question. So,
Yes, please.
um, when to intervene and what to provide the feedback? What to provide the feedback you answered from the machine. But when to intervene is still a tricky question because we may make them to explore a little bit, or we can actually give them the hint immediately. So,
Yes.
how to decide this threshold, which is good enough for a different types of learner, so that they
Yes.
learn it better than solve it better?
It's an excellent question. And then I would say that's $1 million question because we just submit the proposal today to NSF to actually do whatever do exactly what you said. So, the current, to answer the question, the currently SIMI student is actually the Mr. Williams, right? So Mr. Williams is actually driven by model tracing technique. Okay. So the Mr. Williams has a production rules that actually features how to teach, right? So the production may say something like, right? So if semi student passes one-step equation quiz,
Mm.
then teach two-step equation, right?
Yeah.
Or
Mm.
this production may say something like, um, when the semi student fails on the quiz and the human student does not know how to solve,
Mm.
then the human student should review the worked out examples,
Mm.
right? So that's kind of production, right? The featuring how to teach. So to answer your question, the timing of providing the feedback at this moment
Mm.
is when any of these event happens, right? Like semi-student passes quiz, right?
Mhm.
So then some kind of production fires, right?
Mhm.
Or the human student cannot actually provide the feedback, I mean the hint, right? So that then another production may fire,
Mhm.
right?
Yeah.
So it is more like the right. It's yeah, it's a production based the knowledge, and then whenever any of these production fires,
Mm.
then the Mr. Williams actually provide the suggestions, right?
Yeah.
But then the better idea is to actually maybe we may use the reinforcement learning to understand, right, when and how, what kind of scaffolding should be provided, right?
Yes.
So
Yeah.
yeah, that is exactly the things we actually
Yeah.
propose.
I completely understand that it's very tricky to answer that. Yeah.
Yes, 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 yes. So it is also right the trade-off between the amount of intervention, right? Machine provides and how much freedom or
Mm.
we provide. It is sometimes called like a productive failure, right? Let
Yeah.
students fail, right? And then let them learn from their failure, right? So then it's been a long-standing discussion in the literature, like to understand when to intervene, right?
Yeah. Yes.
So it is not an easy, actually, the question to answer, right? Uh,
Yeah.
yeah, and then this is something we have a room to study.
Yes. That sounds good. Thank you. Thank you
Yes.
so much for such a wonderful talk and such a
Okay.
wonderful.
Well,
Yeah.
thank you so
Yeah.
much.
So for attendees, please stay back. Your feedback is very valuable for us. So once the feedback screen is displayed, please scan it and please send the feedback. Yeah. Yeah. The next APSC webinar is also there. So it is on computational thinking and AI in schools, what we can do better. So it's by Professor Valentin. And then it will be in the 20th November. So please do attend. So now you can provide the feedback. It will be displayed. Thank you everyone for attending this seminar. Thank you, Professor Nabaru, once again. Yeah, see you.